Imagine this. You pour a glass of hot water and a glass of cold water side by side. Which one do you think will freeze first? The answer might just blow your mind. Welcome to a world where the ordinary hides the extraordinary, where kitchen experiments defy logic, and the air you breathe is a stage for invisible forces at play. Today, we're pulling back the curtain on the secret science woven into your daily routine, unlocking the mysteries behind the simplest things you do. From the way ice cubes clink in your drink to the miracle of flight overhead, physics and chemistry are the hidden engines powering your world. Get ready to have your curiosity ignited. These 10 tell me why facts about these physics and chemistry that will transform how you see the science in everyday life. Let's dive in and uncover the wonders all around you. Glass is a solid material, yet it's almost invisible to our eyes. You can press your hand against a window, look through it, and see the world outside as if there's nothing in your way. But why is that? What makes glass so unique among solids that it lets light pass through, while most other materials block our view completely? The answer lies deep within the structure of glass itself. Unlike metals or crystals, glass is what scientists call an amorphous solid. That means its atoms aren't arranged in neat, repeating patterns. Instead, they're jumbled together in a random, disordered way, almost like a frozen liquid. This lack of order creates large gaps in the energy levels that electrons in the glass can occupy. When light hits glass, it's made up of tiny packets of energy called photons. For glass to absorb these photons, the energy of the light has to match the energy needed to move an electron to a higher level. But in glass, the gap between these energy levels is much bigger than the energy carried by visible light. So, visible light photons simply don't have enough energy to be absorbed. They pass right through, just like a baseball flying through a sparse forest without hitting any trees. That's why you can see through a window, but not a wall. In a wall, the atoms are packed in a way that allows them to absorb or scatter visible light, blocking your view. Glass, on the other hand, lets most of the visible spectrum pass through, making it transparent to our eyes. However, not all light gets a free pass. Ultraviolet or UV light carries more energy than visible light. This extra energy is enough to excite the electrons in glass, so UV light gets absorbed instead of passing through. That's why sunglasses are designed to block UV rays. They protect your eyes from the harmful energy that glass alone can't stop. So, the transparency of glass isn't just a simple trick of nature or a matter of being clean and clear. It's a fascinating result of quantum physics, the strange rules that govern the tiniest particles in our universe. Scientists study these properties in labs to create new types of glass for everything from smartphone screens to powerful telescopes. So next time you gaze through a window, remember, you're not just looking through a simple sheet of material. You're witnessing the wonders of quantum mechanics in action, allowing you to see the world in a way that's both ordinary and extraordinary at the same time. The Mpemba effect, hot water freezing faster than cold, sounds impossible, but it's real. This strange phenomenon has puzzled scientists and curious minds for centuries. Imagine pouring 2 glasses of water, one hot and one cold, and placing them both in the freezer. You'd expect the cold water to freeze first, right? But sometimes the hot water wins the race. How can that be? Let's break down the science behind this counterintuitive effect. Hot water loses mass through evaporation, giving it less to freeze. As the hot water sits, steam rises and some of the water literally disappears into the air. This means there's less liquid left to turn into ice, so the freezing process can happen more quickly than you might expect. It churns with convection currents, shedding heat faster than cold, stagnant water. These swirling currents help distribute the heat throughout the liquid, allowing it to cool down more evenly and rapidly. In contrast, cold water tends to just sit there, cooling slowly from the outside in. Hot water also has fewer dissolved gases, which slightly raises the freezing point for cold water. When water is heated, gases like oxygen and carbon dioxide escape, leaving the hot water purer. This subtle change means cold water, with more dissolved gases, actually freezes at a slightly lower temperature, giving hot water a tiny head start. Sometimes, hot containers melt frost in the freezer, improving heat transfer. When you put a hot beaker on a frosty shelf, it melts the ice beneath it, creating a better connection with the cold surface. This allows heat to escape from the water even faster, speeding up the freezing process. Add it all up, evaporation, convection, gas loss, and environmental factors like frost melting create the perfect storm for hot water to win the freezing race. Each of these effects might seem small on its own, but together, they can tip the scales in favor of hot water freezing first. Science is full of surprises. The Mpemba effect reminds us that even everyday things, like freezing water, can defy our expectations and spark new questions, which leads us to our next everyday mystery. Stay curious, because the world is full of fascinating secrets waiting to be uncovered. Have you ever stared at a candle flame and wondered why it glows with so many colors? Think of a candle flame like a tiny rainbow painted by heat and chemistry. At the very base, you'll spot a bright blue glow, This is the hottest part, where wax vapor and oxygen meet and burn perfectly, like a well-tuned engine releasing blue light. Move up and the flame turns yellow and orange. Here it's a bit cooler and there's less oxygen, so the burning isn't complete. Imagine tiny specks of soot like microscopic sparks, heating up until they glow yellow hot. That's incandescence, just like the filament in a light bulb. So, the blue is pure chemistry in action, while the yellow is physics. Glowing carbon lighting up the night. Every candle flame is like a science experiment on your birthday cake. Chemistry and physics working together in a beautiful dance. Next time you see a flickering flame, remember, those colors are a secret code, telling the story of heat, fuel, and light. Let's keep exploring. If you enjoyed uncovering the science behind everyday wonders, don't forget to hit subscribe, give us a like, and keep watching for more fascinating explanations. Your curiosity lights up our channel. Have you ever wondered why a rubber duck floats so effortlessly on the surface of your bathtub, while a toy car, even if it's small, sinks straight to the bottom? The answer lies in a fascinating property called density, and it's one of the coolest principles in physics that you can see in action every time you take a bath or visit a pool. Density is a measure of how much mass is packed into a certain amount of space. If an object is less dense than water, it will float. If it's denser, it will sink. This is why a ping pong ball bobs on the surface, while a marble quickly disappears beneath the water. Take the rubber duck, for example. It's hollow inside, filled mostly with air, which makes its average density much lower than that of water. That's why it stays on top, gently rocking with the waves, no matter how many times you push it down. Now, let's look at the toy car. Even though it's small, it's made of metal, which is much denser than water. When you drop it in, gravity pulls it down, and it sinks right to the bottom. The water just can't hold it up. But here's something amazing. Even gigantic steel ships, like aircraft carriers, float. How? Their hulls are mostly hollow, filled with air, which lowers their average density to less than that of water. So despite their massive weight, they glide across the ocean's surface. This is all thanks to the principles of density and buoyancy. Buoyancy is the upward force that water exerts on objects, and it's what keeps things afloat when their density is low enough. Scientists and engineers use these principles to design everything from boats to submarines. So, next time you see something float or sink, remember, it's not just about how heavy it is, but about how tightly packed its material is. Two objects can look the same, but if one is made of dense metal and the other of light plastic, they'll behave very differently in water. From your bathtub to the vast ocean, density is the invisible rule that decides what floats and what sinks. It's a simple idea, but it explains so much about the world around us. So the next time you're near water, try your own experiments. Test different objects, and see if you can guess which will float and which will sink. You'll be using the same science that keeps ships afloat and makes bath time fun. On to the next floating mystery. Have you ever wondered why helium balloons float up, almost like they're trying to escape to the clouds? It's not magic, it's science, and a little bit of fun. Most of the air around us is made of nitrogen and oxygen. Imagine these gases as heavy bowling balls rolling around. But helium? Helium is like a bunch of super light ping pong balls, way lighter than those bowling balls. So when you fill a balloon with helium, it's lighter than the air it pushes aside. The heavier air gives it a gentle push up, just like if you tried to hold a beach ball underwater and it popped up. But if you blow up a balloon with your own breath, it's filled with carbon dioxide and water vapor, heavier than air, so it sinks to the ground. Here's a fun fact. Helium is the second lightest element in the universe, right after hydrogen. That's why it's the champion of floating. Want to see for yourself? Try this. Fill one balloon with helium and another with your breath. Let them go at the same time. Watch the race. Which one wins? The helium balloon, every time. That's why party balloons always soar to the ceiling, making every celebration a little more magical. So next time you see a golden balloon floating by, remember, it's not just floating, it's showing off some awesome science. Ever wondered why iron rusts away, but gold stays dazzling forever? Iron is like that friend who can't resist getting into trouble. It's highly reactive, always eager to mingle with oxygen and water in the air. When iron meets water, it's like a party for rust. The water helps oxygen stick to iron, forming iron oxide, the crumbly reddish-brown stuff we call rust. Gold, though, is the VIP at the party, aloof and untouchable. It's a noble metal, which means it's almost completely uninterested in reacting with anything around it. Gold's electrons are locked up tight, like a safe with an unbreakable code. Oxygen and water just bounce right off. That's why ancient gold coins look brand new, while iron tools from the same era are just piles of rust. Here's a fun fact. The Eiffel Tower needs to be repainted every 7 years to protect it from rust, but a gold statue would shine on for centuries. Next up, why are bubbles always round? Let's find out. Have you ever noticed that bubbles are always perfectly round? Never cubes, never pyramids, just beautiful spheres? That's because of surface tension. The soap film acts like a tiny elastic skin, always pulling itself tight to make the smallest possible surface area. And guess what? For any amount of air inside, a sphere has the least surface area, so bubbles naturally snap into that shape. Surface tension is like nature's magic trick, pulling every bubble into a perfect, efficient sphere. Here's a fun fact. Bubbles can actually join together and share walls, but each little bubble still tries to stay as round as possible. Want to see for yourself? Grab a bowl, some water, and a little dish soap. Use a straw to blow bubbles and watch them form perfect spheres, right in your own kitchen. Now let's look up. What's the story behind those mysterious airplane trails? Ever looked up and wondered about those white streaks behind airplanes? They're called contrails, short for condensation trails, and they're like giant sky scribbles. When a jet engine burns fuel, it spits out hot water vapor and tiny particles. Imagine a superpowered kettle zooming through the sky. Up where planes fly, the air is icy cold. The hot vapor cools in a flash, turning into tiny ice crystals, just like your breath turning misty on a chilly morning. Those little particles act like seeds, helping the ice crystals grow and stretch out into a long, thin cloud behind the plane. If the sky is dry, contrails fade fast, like a puff of breath that vanishes. But if it's humid, they hang around and spread, painting the sky with wispy lines. It's like cloud making in fast forward, all thanks to physics. Fun fact, sometimes so many planes cross paths that their contrails crisscross and create patterns, almost like a giant game of tic-tac-toe in the sky. Now let's melt some ice with a bit of chemistry magic. Ever wonder why cities dump tons of salt on icy roads every winter? It's not just to make things taste better, it's pure science in action. When salt hits ice, it dissolves into sodium and chloride ions. These ions get in the way of water molecules, stopping them from locking together to form solid ice. This sneaky move lowers the freezing point of water, a process called freezing point depression. That means salty water can stay liquid even when it's below 0 Celsius. That's why after a snowstorm, salted roads are safer to drive on, while unsalted ones stay dangerously slick. Fun fact, salt doesn't actually melt ice by heating it up. Instead, it makes it harder for water to freeze in the first place. Thanks to this chemical trick, millions of cars and people can travel safely during winter storms. So next time you see salt trucks at work, remember, it's science keeping you safe. And speaking of science, here's a classic. Hot air rises, cold air sinks. Ever wonder why hot air balloons soar or why you see steam rising from a cup of cocoa? It all comes down to a simple rule. Hot air rises, cold air sinks because of density. Imagine air molecules as a crowd at a concert. When things heat up, everyone gets excited and spreads out, making the air lighter and less crowded, less dense. This lighter, warmer air floats up over the heavier, cooler air below, just like oil rising above water. That's buoyancy in action. That's why hot air balloons lift off the ground, and why old fridges put the freezer on top, so the cold air can sink and keep everything chilly below. When air cools down, those molecules huddle close, making the air heavier and denser, so it sinks, like a heavy blanket settling over your bed. This invisible dance of rising and sinking air shapes our weather, helps us cook, and even makes clouds form in the sky. So next time you see your breath on a chilly morning, remember, density and buoyancy are at work, all around us, even in the air we breathe. There you have it, 10 everyday mysteries unraveled by science. From glass's quantum tricks to salt's icy loophole, physics and chemistry are everywhere. Which fact blew your mind? Let us know in the comments. Hit subscribe for more science secrets and keep asking, tell me why. Thanks for watching, and stay curious.